All right, what's up, guys? It's late. I don't really want to do this now, if I'm being honest with you, but I think I'd rather do it tonight than tomorrow. So, let's try to work through this. This is the last problem from last week's quiz. It's kind of terrible. And I'm not sure my answer is correct here, but I'm gonna just do my best, and I think this is probably what he wanted you guys to do. Now, I don't ask him because, like, I'm a little behind on grading, so I don't really want to draw attention to the fact that I'm behind on grading. Hopefully that makes sense and is understandable. Anyway, so this is the problem statement, right? We have these two wooden discs. They're identical. Essentially, one is just like, you know, rolling down this incline, and the other just, you know, is placed flat on its side and it slides down. Okay, and so they have the same linear acceleration down the ramp. Now, we want to find the coefficient of kinetic friction between the ramp and sliding disc. Yes, that's what we want. I actually thought when I tried this earlier I solved for the static friction coefficient, but it's okay. We'll just do some stuff and see what happens. Okay, so I've made a free body diagram for the one that rolls. The one that slides is hopefully pretty straightforward for everybody by this point. You know, we've done a lot of work with Newton's laws, and I mean, it's also going to work out to be kind of the same as this one here, and so you'll essentially see what that looks like. But let's focus on this one. Actually, you know what? Let's start with something we can do. Let's start with the one, or something we know we can do, we feel comfortable with. Let's start with the one that slides, and I'm just gonna go ahead and change my font size here real quick, so maybe it makes it a little easier to see. Okay, so for the sliding one, we're gonna do this. We're gonna write that the net force in the x direction, so notice I'm calling my x direction the direction that, you know, is down along the surface of the ramp, right? It's going to be mg sine theta, right? And you should you know, make your own diagram and maybe, you know, draw some lines and whatnot to convince yourself that it should be sine theta if that's not clear, but it should be sine theta. And then I'm going to say minus the friction force. This is a kinetic friction force, and this is going to be equal to, obviously, the mass times the acceleration there. And that's that for now. Let's go down a few lines and write out the y equation. Simga, yeah, good. Sigmf. There we go, it's late. Oh, Jesus. Okay, let's try this one more time. Okay, so for the y equation, what we're going to have is we're just going to have that the normal force minus mg cosine theta is equal to 0, right? This tells us that the normal force is mg cosine theta, or rather the magnitude of the normal force is mg cosine theta, right? So we can take that business up here, because we'll need the normal force to get the friction force, right? So this is just then mg sine theta minus the coefficient times what we found for the normal force, which is that. This equals ma. We can clean this up a bit, right? We can say that therefore A must be, we're going to cancel all the masses, right? We're going to factor a little bit, so we're going to say that it works out to be g sine theta minus mu sub k cosine theta, right? And honestly, it doesn't really matter if we interchange the sine and the cosine, because we have this nice 45-degree angle here, right? Which means sine and cosine are the same. Nonetheless, so let's try to be good about this. So we find that our acceleration is this. Okay, this is for the sliding one. Now let's talk about the one that rolls, right? So for the rolling one, and I'll have to go back and forth between the diagram and where I'm typing here, but let's just write out the net force in the x direction first. And I mean, it's going to be essentially identical to the one we just wrote, right? It's going to be mg sine theta minus... Now, here's the weird thing, though. We have to put the force of static friction, okay? And I believe that it ultimately doesn't matter, and, you know, we'll talk about that in a second, but for now, let's try to be careful. and it should be technically the static friction force and corresponding coefficient there. Okay, but notice that this is identical in form to this one, right? So yeah, let's write this out. Or you know what? Even at this point, we can see that for this to be true and for these A's to be the same, that the static friction force has to be the same as the kinetic friction force, right? And that's the weird thing about this. And that's what I'm just gonna assume is the case here. So if I go through, I write this one more time, appealing to the work that I've done before, I can write mg sine theta minus mu sub s now, mg cosine theta equals ma, right? So this just tells me that a must be equal to g sine theta minus mu sub s cosine theta, right? Yeah, and I mean this suggests that mu sub k is equal to mu sub s, right? So the two coefficients are equal. So let's just go ahead and from now on just call them mu, right? So I'm gonna get rid of this and I'm just gonna replace it with a mu, no subscript. And I'll do the same thing here. And there you go, okay? Now we need to think about the torque on it. And I'll just call this my z direction as I usually do. Looking back on this, okay, so there's only one force here that exerts a torque, okay, because the gravitational force emanates from the center of mass of the disk, right? And the line of action of the normal force passes through the center of mass of the disk. The center of mass is where we're taking our rotation axis to be, right? So the only force that exerts a torque is the static friction force. And now technically I should be writing what I'm about to write with a negative sign in front because, you know, I told you that clockwise, you know, torques that make things rotate clockwise should be negative, and torques that make things rotate counterclockwise should be positive. But when, you know, we only have one torque, it doesn't really matter, right? We can be a little looser with our convention, and that's what I'm going to do here. So I'm just going to say that the net torque is RFS. This equals it equals the moment of inertia times the angular acceleration, right? We're told the moment of inertia is just 1/2 mr squared, and the angular acceleration is still the angular acceleration. So I can write this now. I can just plug in that this is mu mg cosine theta, right? That's what we said for the normal force. G cosine theta. Yeah, that should be good. And I can cancel a factor of r on both sides, right? So let's do that. Get rid of this r. Get rid of this r. Oh, and the mass too. Let's cancel that. Why not, right? Let's just go crazy with the cancellations. Okay, so we have this then. We have mu g cosine theta equals 1/2 r alpha. Now, we need to remember that... let me write this out, because I'll probably confuse myself and you if I just talk about it. The no slip condition, right? No slip condition is that A equals R alpha, right? So what we actually have here is we have that this is A, right? So I can take, let me copy this and then just paste it down one line. So I can just write that this is 1/2 A, right? And then what I find is that A is 2 mu g cosine theta, right? Okay, so I found A, in one situation, right, which is this, it's g sine theta minus mu cosine theta. And then I found it down here. And this is what we want, right? We want the coefficient of kinetic friction. Yes. We do. So, okay, so then this is what we do. We just set this equal to this, right? So again, I'm saying that this is one expression we found for the acceleration, and this is another, right? So I'm just going to write that a equals a in essence, right? So I write 2 mu g cosine theta equals g sine theta minus mu cosine theta. And I mean, I can even cancel the g's here, so let me just do this carefully here. So 2 mu cosine theta on the left hand side equals sine theta minus mu cosine theta on the right hand side. I then add mu cosine theta to both sides, right? So I get 3 mu cosine theta equals sine theta. And I find then that mu, right, equals sine theta over 3 cosine theta. This is also known as tangent of theta over 3. Okay, and this is what I'm thinking you're supposed to do here. This is my best guess at what he wanted. So just to deconstruct this a tiny bit, right? The one thing that we have going for us here is that this coefficient of static friction is dimensionless, right? Because we're going to plug 45 degrees into tangent, which should give us 1, in fact, right? Because tangent of 45 is just sine of 45 over cosine of 45, and sine and cosine are the same at 45 degrees. So this should just equal 1/3, right? And that kind of checks out because, you know, mu is supposed to be in general less than 1. And, you know, we get a result that makes dimensional sense, if nothing else. So there you go. I think this is what you're supposed to do. You know, feel free to follow up with me if you have any questions about what happened here. I know it's perhaps a bit confusing. I'm not even sure myself, right? Like, I'm doing my PhD in this stuff, and I'm not even sure. But it's okay, right? It's you sometimes you don't always know what to do. Okay, so there you go. I'll see you guys later on. You know, let me know if you have any questions about this stuff.